Oh yeah. All right. Yes, folks, we're back. Okay, awesome. Welcome back, folks. Spring 2021. We made it. You know the drill. You know how we do here. I'm just going to get right into it. So, I'm going to have a couple of review lectures here that we're going to do. And then we're really going to get into the meat of this class next week. Okay, so reviewing our units. Okay, units, just like in last semester, will be important this semester. And so this is good practice for me, getting used to writing again, right? Okay, so units. The Newton is a kilogram meter per second squared. Okay, great. A joule, of course, is a Newton times a meter, right? Force acting over a distance. So that gives us a kilogram meter squared per second squared. All right. So a watt, unit of power. So that is joule per second. Okay. So Pascal, we remember that's our SI unit of pressure, which is a force per area. So technically that is a Newton per meter squared, which makes that a, let's see here, that makes it a kilogram per meter per second squared. Okay. And so then we get into an ampere or an amp. Okay, so that's a unit of charge. All right. And so that is a coulomb per second, of course, or excuse me, an amp is a rate of charge. Coulomb itself is a charge, which of course I'll just define as an amp second. Okay, so we'll say that's a unit of charge. Okay, a volt is a joule per coulomb, or of course a joule per amp second. And the electron volt, okay, is a joule per coulomb times fundamental charge E, okay? Where hopefully we remember that fundamental charge E is the following. So this is a joule per coulomb times 1.602 times 10 to the minus 19 coulombs. So an electron volt can be used for energy, and so that's 1.602 times 10 to the minus 19 joules. Okay. So hopefully we recall the wave number. So wave number is a Greek letter nu, and specifically I'm going to put a little tilde on here, okay? And this is something that we want to really start recognizing more of in this class. When you see a little tilde over something, it's units of energy in wave number, okay? If we don't see the little tilde, it's units of energy in joules. And really what we're getting at is single joules per one thing, all right? So, and I'll remind you, we get to single joules of one thing from E equals hc over lambda. So that gives me the energy of one single photon or perhaps one single electron, okay? So we've got to remember these fundamental units. So electron volt would be our fundamental unit of energy, okay? And so for the wave number gets a Greek letter nu tilde. This is calculated as 1 over the wavelength, okay? And so because we know that E is hc over lambda, another way that we could calculate wave number would be E divided by hc, okay? And so again, we're going to start seeing energy represented as either joules or wave numbers or possibly even electron volts. So you definitely need to have familiarity converting back and forth into all of these units, okay? And just to give you kind of an idea of the value of these units, okay, if I have 1.602 times 10 to the minus 19 joules per one thing, well, I can scale that up into joules per mole of things, or even kilojoules per mole of things. So this number, 1.602 times 10 minus 19 joules, corresponds to 96.49 kilojoules per mole if I amped that thing up by 1 mole, okay? But also this same value of energy, I'm just going to kind of keep this going here. This same value of energy is 1240 nanometers, so that's infrared, okay? And so how do I convert that to wave number? Well, I could take 1 divided by 1240, and of course convert a nanometer into a centimeter. I'm not showing this as an example. I want you to try this on your own to make sure you get the numbers right. So this 1240 nanometers, which is the same as 96.49 kilojoules per mole if I have a mole of things, which is the same as 1.602 times 10 minus 19 joules if I have one single thing, is 8066 wave numbers, 8066 wave number, okay? And so I want to show you a nice connection here. So again, we've all started with that this is 1 electron volt, okay? So 1 electron volt is 8066 wave number, which is 1240 nanometers, which is 96.49 kilojoules per mole, which is 1.602 times 10 minus 19 joules. Okay. Here is the easy part, the ease of using the electron volt specifically. Okay. So check this out. I know that 1 electron volt equals all of this stuff. Well, what about 10 electron volts? Okay. Well, 10 electron volts, I'll pick one of these numbers to make it easy to start with. 10 electron volts is going to be 1.602 times 10 to the minus 18 joules, all right, which is going to be 964.9 kilojoules per mole, which is going to also be 124.0 nanometers. All right. So I got that 124 because 1240 is 1 electron volt. 10 electron volts is 10 times that amount of energy. So that means it should be 10 times less in the wavelength. Okay. So now what about the wave number? All right. Well, let's do that. I'll just say 1 divided by 124 equals. And so there is that, oops, I wrote 8066. Maybe more like 8065 would be better. Okay. So now this number is telling me 0.000, et cetera, right? Well, in 1 centimeter, there's 1 times 10 to the 7 nanometers. So if I bump this up by a factor of 7, so I'm going to say times 1e to the 7th. Okay, great. And I get exactly what you might have expected. I get 80,600, I'm just going to use the same number of digits, 650 wave number. Okay? So being able to quickly scale your way through all of these units will be very useful. All right? Okay, so that's a review of units. Quantum mechanics, that's what we're learning this semester. Okay? This applies to objects of very small mass and very small energy. Okay? Hence, needing to be able to use these units like electron volt or wave number or single joules. Okay? So objects of very small mass and very small energy, like electrons or photons. Okay. So where does the term quantum come from? It means quantized. Okay, and this is something we're going to be exploring throughout the semester. We're going to be seeing processes which occur with very specific quantized amounts of energy. Okay, and so the constant, so we're still going to use Boltzmann's constant quite a bit. Sorry, I forgot to put this on this review page. So K Boltzmann. Don't forget K Boltzmann. Okay, so K Boltzmann, right, is the same as the gas constant. We recognize they're just different by a factor of a mole. Okay, so K Boltzmann is 1.38 times 10 minus 23 joule per Kelvin. Okay, so now Planck's constant. This is going to be our constant of choice this semester. 6.626 times 10 minus 34 joules times seconds. Okay, and really I actually just lied to you. Our constant of choice is going to be h bar. Okay, so that's Planck's constant, h, with this little like slash through it. We call it h bar. So what is h bar? Okay, well, it is Planck's constant divided by 2 pi. Okay, so let's see here. So that has a value of, so we say 6.626 e 34 negative. Okay, and if I divide that by 2 pi, yep, it's about 1.05 or so. So 1.05, let's call it 5, times 10 minus 34 joules times seconds. Okay, so the big thing to recognize, Planck's constant, or h bar rather, is h divided by 2 pi. And as a matter of convenience, we shall see that using h bar is more convenient than using just Planck's constant, having that factor of 2 pi already in there. Okay, great. So moving on. So just a quick flash review of Stepmech. Okay, so we recall that these are our 4 molecular modes of motion: the translational, the rotational, the vibrational, and the electronic. Okay, so we recall that the energy levels of the electronic, so if let's say this is energy level 1, 2, 3, 4, 5, etc. Okay, they get closer together as we go higher up. We're going to prove that mathematically. And the energy spacing for a typical electronic transition, I'm just going to give this in terms of electron volts. This is about 1 to 10 eV. Okay, and so if you remember that 1 electron volt, right, that was 1240 nanometer. That's IR, but 10 electron volt, you know, that goes all the way up to 124 nanometer. So we'll see that that's going to really predominantly span the visible and ultraviolet range, are the predominant ranges that that spans. Okay, and so now I'm not sure. And if you recall, if I were to zoom in on this very first energy level, this first electronic energy level, that small little box here would then correspond to like the entire vibrational energy spectrum. Okay, so we would get now a whole host of levels. So, oops, let's suppose I miscopied this. So level 1 is down here, and then 2 and 3 and 4 and 5, etc. Nope, I'll take that back. Whoops. I missed a whole bunch of lines here. So we recall the vibrational levels are evenly spaced. So there was a whole bunch of missing lines there. So that'd be like level 1, 2, 3, 4, 5, etc. Okay? And a typical value, a typical energy spacing for those vibrational levels will be more like 0.1 to 1 electron volts. Okay? So definitely in that IR region. Okay? And again, these are just general cases, right? And if I were to zoom in on that very first vibrational level, we would see a whole host of rotational levels. And once again, I'm sorry, folks, I'm just realizing how badly I miscopied these diagrams. So these diagrams aren't accurate, but that's okay. For now, all I'm doing is just reviewing what our typical energy spacings would be. Okay. So for the rotational energy levels, a typical spacing is going to be on the order of milli-electron volts. So something like 0.001 electron volt. And that puts us into the microwave regime of the spectrum. Okay? And then recall the translations here, that those levels are so finely spaced together that they make what we call the continuum. Okay? Continuing along in our review of statistical mechanics, so recall the Boltzmann distribution, okay, which says the number of particles in state I divided by the number of particles in state J equals, let's all use the E raised to the power negative EI minus EJ, so the difference in those energy levels, all divided by K Boltzmann T. Okay, and then the whole quantity is negative, right? And so if we remember here, the higher the energy of a state, the lower its population. Okay, so the electronic states, right, we recall that everything is in the ground state in the electronic state. Because it's got such a high energy state, there's not enough energy at room temperature to populate an upperlying electronic state. Okay, the higher the temperature of a state, the lower its population. Okay, or really I should say the higher the temperature of the state, the more likely a higher energy state is populated. Okay, so some reason I copied that incorrectly. So the higher the temperature of a state, the more likely a higher energy state is populated. So as we increase the temperature of a material, it can excite or it can get into higher levels. Okay, and of course more states are populated if they are closer together. So that's like the translations, right? They get really finely crunched together. Okay, so if we were to look at 0 Kelvin, hopefully remember at 0 Kelvin, everything will be in the ground state. So this kind of shaded area represents 100% of my particles. Okay, at 298 K, there's some type of distribution. Okay, and that distribution might look something like this. Okay, it's going to have a Boltzmann distribution, right? So there's going to be some curve, right? And I kind of drew this curve on its side, but we recognize at 298, of course, depending on if we're talking about electronic, rotational, or vibrational, this is what the populations will look like. And this figure that I've drawn here is a good example for the vibrations as well as the rotations as well as the translations. Okay, the vibrations, the rotations, and the translations will have some kind of distribution, mostly the rotations and the translations. Recall the vibrations, like 99% of everything is in the ground state, and maybe 1% of everything is in the second highest state. Okay, so actually I'll take that vibrations off the list there. Okay, getting back into the saddle, folks, getting back into lecturing. And if such a temperature could exist infinite Kelvin, then all of these states would be thoroughly populated. Okay? Get out of there. Remind me later. Okay. And so another way we can kind of think of this postulate number 2 that I did a bad job describing, the higher the temperature of a state, so as we increase this 298K temperature, what we would see is this distribution. So let's say the most populated state is state number 3. If we increase the temperature on this system, then the highest populated state is going to move up to upper levels. That distribution is going to shift up to higher levels. Okay? But again, big thing to recognize here, the Boltzmann distribution, and I'm going to put a proportionality sign, E to the negative energy, and I'm just going to write that out, divided by K Boltzmann T. So I want us to be able to recognize when we see something is based off of Boltzmann. And when we see that something is based off the Boltzmann distribution, we should recognize that we're not really talking about a single particle. We're talking about a large number of particles, right? That's what the Boltzmann distribution is all about. Okay, so a nice little review here on the electromagnetic spectrum. Okay, so recall, visible light occurs over a very narrow range of wavelength between 700 nanometers to roughly 400 nanometers and goes as Roy, G, Biv, right? Red, orange, yellow, green, blue, violet. Okay. If we go to higher energy from the visible, we get into the ultraviolet, about 10 minus 7 nanometers. Okay. And if we keep going, we get into this region called the vacuum ultraviolet. And the reason why that's called the vacuum ultraviolet is because these wavelengths will ionize oxygen as well as nitrogen, mostly oxygen with 100% quantum efficiency. So to use this type of radiation, we typically need it to be under vacuum because oxygen will absorb all of that radiation. As we keep going, we get into X-rays. Okay, and notice here that under X-ray, we get core electron excitation. So that's some pretty high energy stuff. And we're going to call this, we're going to note that this corresponds to X-ray photo electron spectroscopy. We're going to learn about that type of spectroscopy as we go. Okay, and we're not really going to go any past X-rays, though you notice here if we got into gamma rays, we would be getting into nuclear excitations. Okay. Backing up here, back to the visible. Okay, notice here that's referring to electronic excitation. And of course, that electronic excitation also extends into the ultraviolet and the vacuum. Okay, so really that's related to electronic transitions. So as we go less in energy and bigger in wavelength from the visible, we get into the near IR and then into the far IR. And those correspond to molecular vibrations, okay? And as we go into even lower energy, we get into the microwave, and that corresponds to molecular rotations. So this semester, we're really going to be hitting this hard, going after these molecular modes of motion and their corresponding region on the electromagnetic spectrum, okay? Beautiful. Carrying on. So now we're kind of getting into this first bit that's somewhat new, okay? And I think maybe you might have talked about blackbody radiation and Planck's law somewhat in some of your other physics classes. But just in case you don't remember, just in case to go through that, all objects above 0 Kelvin emit thermal radiation. They have to, okay? So I am an object. I'm not 0 Kelvin. I'm about 310 Kelvin. And because I'm about 310 Kelvin, I emit thermal radiation. That thermal radiation just so happens to be infrared for an object that's about 300 Kelvin. Okay? As we increase the temperature of that object, the type of radiation that object will emit becomes more energetic as the object becomes hotter. So in fact, you're used to hearing that IR radiation is thermal radiation, right? Technically, all EM radiation is thermal, okay? You're used to hearing that infrared is thermal radiation, and that's just a very human-centrist idea because humans just so happen to be a temperature that emits infrared. Technically, all electromagnetic radiation can be classified as thermal radiation, okay? So an ideal emitter of this thermal radiation is called a black body. And black body radiators follow the Planck distribution, okay? Or known as Planck's law. So this equation right here, okay? So this rho, this is given as energy density. And as you can see that is a function of wavelength as well as temperature. So the energy density depends on what your wavelength is, and it also depends on what the temperature is, okay? So the energy density will have units of joule per meter to the 4th power. However, if we were to integrate this energy density, so if I integrate this from some T1 to T2, this rho as a function of lambda and T times d lambda, well, d lambda has units of meters. The Planck distribution has units of joules per meter to the 4th power. So when we carry out this energy, we get truly, if we carry out this integration, we truly get an energy density in joules per meter cubed, okay? So these graphs right here are the Planck distribution here that have been plotted. And so what this integral means is if I were to take the area under one of these curves, which is the same as taking this integral, right? I get joules per meter cubed, okay? I get the energy density. I also want to point out here, I'm not going to derive this Planck distribution, but I'm going to note here, take a look at this chunk, okay? It's Boltzmann, right? That is a Boltzmann distribution, okay? That is E raised to the power. And it's not negative in there because there's some mathematical manipulations that have taken place, okay? Unless, of course, I made a mistake, which is entirely possible. We'll just go for it the way that I have this written for now. But you notice here that it is E raised to the hc divided by lambda. Well, remember, energy equals hc divided by lambda. Okay, that is energy. So this is E, it's still E raised to the energy divided by K Boltzmann T. Okay, so it is a Boltzmann distribution, but now this energy is hc divided by lambda. It's the energy of a photon. Okay, so I've got this really cool blackbody simulator right here that I've also linked into the Canvas site. And this is to show you what happens to ideal blackbody radiators as you change the temperature. So for now, this little slider here, so this is like a cool manipulate thing. So the slider here is at the temperature of the sun, approximately 6,000 Kelvin or so. And our sun emits white light. The reason why it does that is because it is an object that is 6,000 Kelvin. It emits all of the visible wavelengths as well as some ultraviolet. So you can see the tail end of this distribution goes past the UV. So our sun obviously emits some ultraviolet. You knew that. But our sun also emits a lot of IR, which you can see that goes past the visible region. Okay. And so even though it's peaking like in the green, to our eyes, the sun kind of appears yellow, okay? So this is really cool. As I turn the temperature down, notice here that not only does the energy density decrease, but the peak wavelength also decreases, right? So now if I go to like a light bulb, maybe a typical light bulb, that's 3,000 Kelvin, so you can see that orange color there, that's the color that it would appear to our eyes, okay? So as I go past, I can see we get that nice like yellow sun color, kind of, okay? As I get colder and colder, it's shifting out to the red end of the spectrum. And I can zoom in on this scale here. So you can see this light bulb, this 3000 Kelvin, it's actually kind of peeking out into the infrared, but it appears kind of orange because the tail end of this distribution is like into the blue and green. Most of the distribution is into the red end of the spectrum. And if I keep turning this all the way down, maybe we turn this down to a temperature that's like, you know, that of the Earth, about 300 Kelvin or so. You can see it's not very luminous at all because it's cold. It's only 300 Kelvin. And so if I zoom way in on this scale here, assuming that I can, look, the tail end, there it is. And maybe if I turn the temperature just up a little bit, yep. So that's a 350 Kelvin object. It's not emitting any visible light. It's only emitting infrared light, okay? And this is also really cool, so I'm going to turn the scale way down. If I go way up to like Sirius A, this is a blue dwarf star. Check it out. It's about 10,000 Kelvin, and look, it would appear blue to our eyes. And if you look at this, it's still emitting all the visible lights, but it's predominantly emitting blue and ultraviolet, okay? So in this black body radiator, because this is based off of Boltzmann, we recognize that this is an ensemble property. This is a property of a mole of objects, okay? So if I keep going on now, just to review, I'll remind you more of our statistical mechanics, degrees of freedom, right? Recall we get 1/2 K Boltzmann T, 1/2 kBT per degree of freedom. So if I talk about a linear molecule right here, okay, we recognize all molecules are atoms will have 3/2, I used RT, so I'll stick with the RT, has 3/2 RT degrees of translational freedom, right, from motion in the X, Y, and Z directions. So we get 3/2 RT degrees of freedom there. But so this linear molecule, it can rotate in 2 unique dimensions, as noted here in this figure, okay? So that's going to give me another 2/2 RT, giving us 5/2 RT for linear molecule, okay? Recall a nonlinear molecule will have 3 RT. So it has 3/2 RT translational freedom, and there's 1, 2, 3 degrees of rotational freedom, so that's also 3/2 RT. So why am I reviewing this? Well, remember, recall solids, heat capacity of a solid, okay? And I'm going to draw the cube here. And if you recall, in a solid, and what I will call a perfect solid, perfect crystalline solid, it can vibrate in a dimension coming out of the board or a dimension going into the board. It can go to the left, it can go to the right, it can go up, and it can go down. And each one of those gives me what I'll call 1/2 RT, okay? So 1/2 RT, 1/2 RT, et cetera, for a perfect solid, giving me 6/2 RT. And then we recall that the derivative of internal energy with respect to volume, the derivative, I did that wrong. This is why I need a review. The derivative of constant volume internal energy with respect to temperature gives me CV. So if I take the derivative of this, I get, 3R. 6/2 equals 3. So I get 3R. Okay? So you can see now heat capacity of a solid, CVM, equals 3R. There it is. But what is this little chunk right here? Okay? So this chunk is a function of temperature. It's what we call one of the Einstein equations. Okay? And what I want to point out, look, it's another Boltzmann-like distribution. That's kind of all that I want you to recognize from this. It's another Boltzmann-like distribution. So the heat capacity of solids is another population of states. Okay. So how do we get that that's a Boltzmann distribution? Well, recall this theta E. That's the Einstein temperature, which is h nu divided by k. Okay. Well, remember, if E equals hc divided by lambda, it also equals h times nu, h times frequency. Okay. I see you back there. So when I look at this exponential here, this e to the theta e divided by 2t. So check it out. We recognize that h nu is energy. Okay? So look, this just becomes e to the 1/2 energy divided by k Boltzmann t, which is kind of cool. Okay? And now, I talked about this a little bit last semester, but there are slight differences between the Einstein temperature and the Debye temperature. And I don't want to get into a lot of those details. They both do a really good job at predicting or approaching this 3R when you're at a sufficiently high temperature. Okay? So there's just, obviously subtleties between the two formulas and equations at lower temperatures. And I don't want to spend a whole lot of time getting into that. The main thing to review is the heat capacity of a solid at room temperature will be 3R. However, at low temperatures, this is where interesting quantum mechanics type stuff is occurring, okay, via the Einstein distribution or even the Debye distribution. Okay, folks, so that is a good place to leave off for video number 1. I will pick up with wave-particle duality in video number 2. Hasta luego.